Yeah.
We are not expecting too many other people. We're talking about it in Swedish under the circumstances. We are still not in proper fall semester, so we should start with the seminar. Today will be given by Daniel and Summ, who has performed his master thesis in Aachen for 5 months. And, you have done computations in the next two minimal supersymmetric standard models. So please.
Yeah, thank you for the introduction. As already mentioned, my name is Benjamin Summ, and I will be presenting the work that I performed at RWTH Aachen University in the group of Professor Michael Klemmer under the supervision of Dr. Alexander Vogt and with my former supervisor here, Tommy Olsson. The presentation is about Higgs mass calculations in the next to minimal supersymmetric standard model and is organized as follows. I will start by telling you why supersymmetry is an interesting extension of the standard model and by giving sort of the minimal background you need to understand the calculations. Then I will introduce the two standard methods that are used to calculate the Higgs mass in supersymmetric models. And then I will discuss a rather new method called flexible EFT Higgs, which is what I mainly worked on and what I extended. After discussing these methods in general, I will specify the physical scenario that I was interested in and tell you about my extension, which is basically a matching procedure. And if you don't know what a matching procedure is, I will elaborate on that later. Once we know how to do the matching, I will tell you how to perform the Higgs mass calculation in terms of a boundary value problem. And then I will show my main results and discuss them. So let's start by looking at why supersymmetry is an interesting extension of the standard model. So roughly 5 years ago, shortly before I started studying physics here at KTH, there was a big splash in the news coming from the LHC. And it was about the discovery of the Higgs boson, and you could tell that it was a big deal because it made it into the news. But also for physicists, it was a big deal. And as you might know, it's because the Higgs breaks the electroweak symmetry and thus generates masses for the fundamental fermions and the mediators of the weak force. However, as you also might know, once we solve a problem in physics, we tend to introduce new ones. With the Higgs, the problem is not really within the standard model, but rather once we go beyond the standard model. So why would we want to go beyond the standard model? Well, the simple answer is because the standard model doesn't explain everything. For example, the standard model only touches upon 3 of the 4 fundamental forces that we know of. It doesn't touch upon gravity at all. Also, there's overwhelming evidence that there's something called dark matter in the universe, and the standard model doesn't give us any dark matter candidate. And finally, we know that the expansion of the universe is accelerating, and we attribute this to something called dark energy, but the standard model doesn't really tell us what that is. So in order to solve these problems, or at least one of them, we would like to introduce some new physics that usually lies at a higher energy scale than the electroweak scale, and somehow couples to the Higgs boson, either directly or indirectly. This introduces quantum corrections to the Higgs mass that tend to be of the energy scale of the new physics. And if this energy scale is large compared to the electroweak scale, which is around the Higgs mass, then it becomes very difficult to maintain a Higgs mass of 125 GeV in your theory. One way you could do this is, so maintain this Higgs mass, is to arrange your quantum corrections in such a way that they cancel. And this includes some kind of tuning of couplings and masses of the new physics, and such a tuning usually indicates some kind of symmetry. That leads me to the next question, which is, what is supersymmetry, or can supersymmetry be dissymmetry? In its cure, supersymmetry is simply a symmetry between bosonic and fermionic degrees of freedom in a theory. And the degrees of freedom that are related through supersymmetry are called superpartners. Whenever supersymmetry is exact, which means it's not broken, then these superpartners have exactly the same masses. And it turns out that this is the kind of symmetry that protects the Higgs mass from getting quantum corrections. In fact, if supersymmetry is exact, the Higgs mass doesn't get any quantum corrections at any order in perturbation theory, and this is the non-renormalization theorem of supersymmetry. This sounds very nice, however, there's a little catch, which is that the field content of the standard model is not sufficient to actually make a supersymmetric theory. So, in order to have a supersymmetric theory, we, for example, need two Higgs doublets, one that couples to down-type quarks and charged leptons, and another one that couples to up-type quarks to generate the masses. We also would need to introduce a spin-zero boson for each chiral fermion in the standard model, and a Majorana fermion for each gauge boson in the standard model, in order to make it supersymmetric. And that's a lot of new particles. And also, if supersymmetry is exact, as I told you, these would have the same masses as the standard model particles. So we would expect there to be a spin-zero boson with the mass of the electron. Such a particle would have shown up in experiments, and we would know about it. Therefore, supersymmetry cannot be exact in nature if it is realized at all. And that brings me to the picture that I always had in mind while I was working on this project, which is that we have some theory, which we assume to be supersymmetric, that is valid to a very high energy scale, maybe the Planck scale. And then at some scale, the supersymmetry breaking scale, which I call M-SUSY, supersymmetry is broken, and some of the particles in the theory get masses of the order of this supersymmetry breaking scale, whereas other particles maintain masses of the electroweak scale. And the theory that only includes the light degrees of freedom and their interactions can be viewed as a low energy effective field theory, and it's kind of this theory that we probe in experiments. I should also point out that because supersymmetry is broken, in this scenario, the Higgs actually gets quantum corrections again, and they are usually of the size of the symmetry breaking scale. Now, with this in mind, let's look at the standard methods for Higgs mass calculations. So the first method I want to talk about is the fixed order calculation. This is your standard perturbative quantum field theory calculation. You decide on calculating the Higgs mass to a certain order in perturbation theory, you draw all the Feynman diagrams, and you simply calculate. This is good because there are no approximations necessary other than the usual perturbation theory approximation. However, as you might know, once we go to loop level, we have to renormalize our theory, and the renormalization tends to introduce logarithms of the form log M-SUSY over M electroweak. If these two scales are separated by a large amount, then these corrections can be very large, and in fact the truncation error in the perturbation series can be large even if the couplings are small. And this is what we see in this plot. Here we have the theoretical uncertainty in fixed order Higgs mass calculation at 2-loop as a function of the supersymmetry breaking scale, and as you can see, this uncertainty grows with the supersymmetry breaking scale. So the fixed order calculation is really only precise whenever the supersymmetry breaking scale is around the electroweak scale. Luckily, there's another method that can be used, which is called the effective field theory calculation. In this method, you basically assume that the supersymmetry breaking scale is much larger than the electroweak scale, so that some of your particles are much heavier than the others. And you take your path integral in quantum field theory, and you integrate out the heavy degrees of freedom. This has to be done perturbatively, and you end up with an effective Lagrangian that includes operators of all the mass dimensions. So there are operators of mass dimension 5, 6, 7, and so on. However, the new operators of higher dimensions are suppressed by the heavy scale, and therefore they can usually be neglected, and we only include operators up and including mass dimension 4, which then yields the usual textbook approach to quantum field theory. Now, once we have our effective Lagrangian, we need to calculate the parameters of the effective field theory from the parameters of the underlying theory. This is done through what is called a matching. So in this matching, you decide on a scale, called the matching scale, at which both the effective field theory and the fold theory are assumed to be a good description of the underlying physics, and you set equal the one particle irreducible correlation functions with light external particles in the two theories. This gives you an implicit equation for the couplings of the effective field theory at the matching scale. And what you get from these equations is something of this form, which is the coupling in the effective field theory equals the coupling in the full theory plus some finite renormalization. And this finite renormalization is called a threshold correction, and it accounts for the fact that the renormalization group evolution of the couplings in the effective field theory should not depend on your choice of the matching scale. Unfortunately, since we neglect higher order or higher dimensional operators in our calculation, we also neglect terms that are suppressed by m electroweak squared over m SUSY squared in our Higgs mass calculation. And this is what you can see in this figure. So now we see the theoretical uncertainty in the Higgs mass calculation in the effective field theory approach as a function of the supersymmetry breaking scale. And as you can see, for low values of the supersymmetry breaking scale, the theoretical uncertainty is rather large. This is exactly the opposite behavior to the fixed order calculation. So now that we know that there are two different approaches which work well in different regimes of the values of the supersymmetry breaking scale, it is natural to ask, can we come up with a method that has a constant theoretical uncertainty throughout the whole range of possible supersymmetry breaking scales? And the answer is yes, we can, and the method is called flexible EFT Higgs. It was introduced by Arthur, Park, Steutner, Stöckinger, and Vogt, and it is an effective field theory type approach in which the effective field theory is always the standard model. However, instead of fixing the quartic self-coupling of the Higgs in the standard model through a matching of correlation functions, it is fixed through what I call a pole mass matching. So what they do is they take the Higgs pole mass in the full theory and in the effective field theory, and they set them equal at the matching scale. This gives an implicit equation for the quartic self-coupling of the Higgs in the standard model, which you can solve. The good thing about this pole mass matching is that you are no longer neglecting the m electroweak squared over m SUSY squared suppressed terms. And the reason is that when you calculate the pole mass in the full theory, you are not throwing away any higher dimensional operators or anything like that, and you are including these terms, these suppressed terms, in the quartic coupling of the Higgs. And here you can see the theoretical uncertainty of a Higgs mass calculation using flexible EFT Higgs as a function of m SUSY, and as I said, it's roughly constant. So now that we know how this method works, it was my task to extend it to a scenario where the effective field theory is not the standard model. So I started by looking at the next to minimal supersymmetric standard model, and specifically the Higgs sector. You can see the Higgs potential here. And we have two Higgs doublets, HU and HD, because we need two Higgs doublets in every supersymmetric theory, as I already mentioned. And there's also one extra gauge singlet. Now, in order to give masses to both the up-type quarks and the down-type quarks in charged leptons, both of the Higgs doublets have to attain a vacuum expectation value, VU and VB, and these are related to the vacuum expectation value of the standard model Higgs through the relation that you see here, where V is the full vacuum expectation value of the standard model Higgs. We furthermore parameterize the Higgs sector by introducing a parameter called tam beta, which is simply the ratio of the two vacuum expectation values. Also, we specialize on a scenario where the Higgs potential is CP conserving, and that leaves us with 3 CP even neutral mass eigenstates, 2 CP odd neutral mass eigenstates, and 1 charged mass eigenstate. Since we have so many Higgs bosons, it is interesting to ask, what is the Higgs boson, or what is the standard model Higgs, and what is the Higgs that we have actually measured? And there is a condition called the alignment condition or alignment limit that you can put on these mass eigenstates to identify a standard model like Higgs. And the condition is that if one of the CP even neutral mass eigenstates coincides with the state that gets the full standard model vacuum expectation value, then this has the same couplings to gauge bosons and standard model fermions as the standard model Higgs, and therefore behaves like the standard model Higgs. And it is the mass of this Higgs boson that we are interested in calculating. further specify the scenario, we make our singlet heavy with the mass of the supersymmetric breaking scale, but leave the two doublets light. And we also leave all of the usual standard model particles light, and their superpartners become heavy. This means that the appropriate effective field theory is a type 2 Higgs doublet model with this Higgs potential. In order to calculate the Higgs mass in this effective field theory, we need to fix all of the parameters, so the 7 quartic couplings, lambda 1 to lambda 7, and the 3 quadratic couplings, m11 squared, m22 squared, and m12 squared. 2 of these can already be fixed through the electroweak symmetry breaking equations, and we choose these to be m11 squared and m22 squared. The remaining ones have to be fixed through a matching, and I will start by describing the matching of the quartic couplings at tree level. So since the singlet is very heavy compared to the doublet, there's basically no singlet doublet mix-in, and therefore the mass eigenstates of the singlet and the gauge eigenstates coincide, and we can work in the gauge spaces. This makes the matching easier because we simply have to look at the Higgs potential of the NMSSM and find all the vertices that can give us a quartic Higgs interaction by expanding one heavy propagator in powers of the momentum squared over the mass squared. And the reason is that in a low energy theory, the momentum transfer is of the order of the electroweak scale, whereas the mass of the heavy particle propagating is of the order of the supersymmetry breaking scale. So the terms that we neglect are of the order m electroweak squared over m SUDI squared, which is exactly what you do in a normal matching. However, to calculate the Higgs mass to the desired precision, it is not sufficient to have a tree-level matching, so we actually need to match at one loop. And that's more tricky than just matching at tree level because you have more vertices that can contribute, and also you have to calculate all kinds of field strength renormalizations and so on. So we cheat a little bit. What we realize is that the threshold corrections of the 2x doublet model to the minimal supersymmetric standard model, so the MSSM, are already known, and the NMSSM differs from the MSSM only by the inclusion of the singlet and its superpartner. This basically gives us two new couplings that could contribute to the threshold corrections. These are called lambda and kappa, and in our scenario they are small. They are of the order of 10 to the minus 1 or 10 to the minus 2, and furthermore, they contribute to the threshold corrections quadratically. So if we simply neglect these contributions, we make an error of the order of 10 to the minus 2 or 10 to the minus 4, and this can be neglected at the precision that we are interested in. So for the quartic couplings, we simply use the already known threshold corrections. However, we also want to use a pole mass matching so that we don't throw away these suppressed terms. And we have 4 Higgs bosons, physical Higgs bosons, that exist both in the fold theory and in the effective field theory, so we can fix 4 parameters through a pole mass matching. These are chosen to be lambda 1, lambda 4, m12 squared, and the ratio of the 2 vacuum expectation values of the Higgs doublets in the effective field theory. Okay, now that we know how the matching works, let's look at the full calculation as a boundary value problem. And here the point is that some of the couplings that we need in order to calculate the Higgs mass in the 2x doublet model are known at low energies through measurement. So they are known in the standard model, or rather in the standard model without the top, so the SM5. These are the gauge coupling, the Yukawa couplings, and the Higgs vacuum expectation value in the standard model. These are fixed by matching the SM5 to the 2x doublet model at the electroweak scale, or rather at the top pole mass. Once they are known, the 2x doublet model is evolved to the supersymmetry breaking scale through the renormalization group equations. And at this scale, 3 things happen. First of all, we fix the input parameters of the NMSSM as the running parameters at the supersymmetry breaking scale. Secondly, we match the 2x doublet model to the NMSSM to calculate the gauge couplings, Yukawa couplings, and Higgs vacuum expectation value in the NMSSM. This is necessary because we want to use a pole mass matching, and the pole masses of the Higgs bosons in the NMSSM depend on these couplings. So once we know these couplings, we can use the matching procedure that I just described in some detail in order to calculate the remaining couplings in the 2-Higgs doublet model. Then the theory is evolved back to the electroweak scale, and we iterate until convergence. In the end, the Higgs mass is calculated at the electroweak scale. So let's look at some of the results that I obtained through this procedure. The first one is what I call the interpolation result. So here we see 3 Higgs mass calculations using the different methods. In red, flexible EFT Higgs at 1 loop. In green, the EFT calculation at 1 loop. And in blue, the fixed order calculation also at 1 loop. The first point I want to make is that flexible EFT Higgs correctly interpolates between the fixed order calculation and the EFT calculation. And by correctly, I mean that it coincides with the respective calculation where that calculation is the most precise one. And I also want to point out that the coincidence of the red line with the blue line for low SUSY scales actually shows that the pole mass matching takes into account the m electroweak squared over m SUSY squared suppressed terms correctly. So more interesting than the interpolation result, in my opinion, is the precision of the different calculations. So here we see the theoretical uncertainties in the Higgs mass calculation as a function of the supersymmetric breaking scale, in red for flexible EFT Higgs, in green for the EFT, both at 1 loop, and in blue for the fixed order calculation, now at 2 loop. And we see that indeed, flexible EFT Higgs is the only method that maintains a theoretical uncertainty that is roughly constant. Unfortunately, we also see that there is no regime in which flexible EFT Higgs is the most precise method of the 3. And that leads me to the following conclusion, which is that if you know that you are in a regime where either the fixed order calculation or the EFT calculation is very precise and you want to calculate the Higgs mass, then by all means you should use that method. However, if you need to scan over a larger range of values for a supersymmetric breaking scale, then you might want to try flexible EFT Higgs. So to summarize, flexible EFT Higgs utilizes pole mass matchings to maintain a constant theoretical uncertainty for all values of the supersymmetric breaking scale, and this works also in this extended scenario. Unfortunately, flexible EFT Higgs is not as precise as the state-of-the-art calculations, and therefore it would be nice if someone would go to higher orders, so to 2 loop with flexible EFT Higgs, and see if we can get an uncertainty that is both constant throughout the whole range and also very small. And with that, I would like to thank you for your attention and answer any questions that you might have.
Yeah, questions. Any questions to Benjamin?
So there are you introduced these new parameters that you're trying to match. So I was just curious, there are so many parameters. Why so many? It seems like a very complicated model.
You mean here in the 2x doublet model? So basically that's, so there are different types of 2x doublet models. This is the type 2 one, but what you do is you do the usual thing. When you write down your theory, you look at all the possible interactions up to dimension 4, and you write down your theory that is compatible with your symmetries and so on. So yeah, obviously we have 2 Higgs doublets, so there are a lot of couplings that you can come up with. But yeah, I mean, in general, supersymmetric theories they do have a lot of parameters, which is, I think, one of the big drawbacks of supersymmetric theories.
So the numerical running that you have done, how did you do that more specifically? Was that on a big computer cluster or?
No, I actually managed to run it on my laptop.
On your laptop?
Yeah. So we use a simple. We know the beta functions.
Yeah.
So we use a simple stepwise method.
Is that like a running code or?
Actually, I'm not sure because this part I didn't implement myself. It's implemented by Alexander Ford.
Oh.
But I think it's limited for something.
Okay. Some standard
Yeah.
solver.
So maybe I should mention that all of this is implemented in a software called Flexible SUSY, which is
Yeah.
pretty standard in this field. So some of the underlying calculations are already implemented, or were already implemented.
But some of the beta functions you have computed yourself.
Yeah. I computed a beta function for one of the parameters that I didn't talk about here, that I introduced myself,
Yeah.
because it caused numerical problems and I wanted to see why. And it turns out that so in the thesis there's a parameter which I define as A, which basically tells you how big the mixing or the splitting between the masses of the two Higgs bosons is. And this parameter also determines the dr bar mass, the running mass of the CP odd Higgs boson. So when this runs negative, then you basically get a tachyon in your theory. And it turned out that this is one of the parameters that causes big problems. So I calculated its beta function to see that there are actually, because it has mass dimension 1, so there are large contributions from supersymmetry breaking parameters that have to be large in order to maintain the scenario. And then, yeah, the parameter.
So how did you compute the beta function by hand or by some?
Yeah, I did, for this one I did it by hand because I know how it is defined, and I have in the code already the beta functions for all the components, so you just have to basically take the derivative and calculate it from there.
Yeah, sure.
I have actually a question. I'm not a particle physicist, I'm curious. So the motivation for this, I understand this is a tool for theoretical work comparing experimental data with different scenarios for extensions of the standard model. Is it like this?
So yeah, it's about
so that you produce this plot ruled out by this theory.
Yes.
So
one of the things that you could go ahead and do with this is exactly to look at exclusions in parameter space, simply because you don't get the right Higgs mass.
But then I'm confused about is that you showed in the end that there's no regime for this parameter super breaking scale where this new method is kind of best.
Right.
And you said, well, the new method is then useful if you want to scan a big thing.
Yeah,
but what do you gain by that? Or that you can kind of be faster by just having a single method and scan the whole thing, so that you don't need expertise in two methods?
Yes.
I
think at this level, it is precisely that. And there is actually a slight issue with this extension of the method. So the original method, I pointed out, is precisely to match some theory to the standard model. And here the point is, and that's why it's called flexible Higgs, that the only coupling that you have to fix in order to calculate the Higgs mass in the standard model that you don't know at low energy is the Higgs coupling itself. So then you can actually use only one pole mass matching and calculate this coupling, and then immediately calculate the Higgs mass. You don't have to calculate any other parameters through a matching at a high energy scale. And one of the points of the method was this flexibility. And so you simply can implement it very quickly. The problem here is that in this scenario, as you already said, you start to get a lot of parameters, and it's just not possible to fix all of them that quickly. So you actually lose some of the flexibility.
So is it in the community as a whole, these kind of tools exist and are available to all researchers, and then some researcher uses this for a particular study, and then...
Right, so now actually I know of 3 groups that are starting an effort to write some code that can do generic matchings between different theories. So flexible SUSY itself, you have to do quite a lot of work yourself to implement this matching between 2 theories to actually do the EFT approach. You can easily do fixed order calculation, but the matching is difficult. So what people are starting to do now, because this EFT becomes more and more precise, because new physics is pushed upwards in energy, They are looking at writing some code that really can do this matching basically automatically. Just you give the two models, and then it calculates the matching. And these codes, of course, in the end, the idea is to make them publicly available so that everyone can use them. Yes.
So I know that when you're comparing LET data with standard model, you often have to go to a very high order to actually get agreement. So if you go to low order, you compare the data, you think that there's some beyond standard model physics that you're seeing, but then you go to higher order and you get agreement. So then, how this plot in particular, how would it? So I can imagine, I know how to go to higher order for the fixed auto calculation.
Yeah.
So there's a systematic way of improving a calculation.
Right.
How does that work for the other two methods?
So for the EFT method, you can include so actually, it's a question of where you think that this scales. If you think that this scale is very high, there's actually no need to improve the effective field theory calculation. I mean, you can do the matching at higher and higher loop orders, and you will gain something in the running, will be more precise. So basically the dependence of the mass on the matching scale will get smaller, but actually most people that I have been talking to in this community say that for high energy scales, basically we are starting to get to a point where the EFT calculation could just be used like this, and it's superior to everything else. For flexible EFT Higgs, there are several things that you can do. One point that I didn't have time to make is that you actually in this plot see still a deviation that is roughly 1 GeV between flexible EFT Higgs and EFT. And the reason for this is that for the matching here, step 3, we actually match these Yukawa couplings also by matching pole masses. And the problem is that everything is calculated at one loop. So when you match these Yukawa couplings, you get one loop contributions, and then they enter the calculation through a loop as well. So you get two loop contributions, formal two loop contributions. And these do not exist in the effective field theory, and they can lead to some problems in the resummation of next to leading laws.
So does that mean that you cannot keep going in the
You can. You can. In fact, it would be better
Uh-huh.
to do this calculation at two loop,
Yeah.
because then if you still do this Yukawa coupling matching at one loop, then it's fine.
Yeah.
So actually, Alexander Vogt, who was my supervisor, he is in the process of implementing flexible SUSY 2.0. And there what they do the same calculation, but they keep two sets of parameters, one at tree level and one at one loop, so that they can do this matching at tree level, and then you do not induce these higher order terms. And then you actually see, unfortunately I don't have the plot, but you do actually see that these two calculations line 2TeV or maybe 2T. So that's one point. And then you can simply go on in the pole mass matching to higher loop orders in the calculations. But you really have to be somewhat careful that you don't accidentally introduce some higher order terms, because they can cause problems.
So, and this is a systematic, you can do it systematically, or is there?
Yeah, it's just a lot of work, because you basically have to implement it twice and keep two sets of parameters. But this can be done systematically, yes. You just have to look at, in my calculation, at what order in my loop expansion does my coupling contribute to my calculation, and then you just match it at one order lower, or, well, it depends what your loop calculation, what the loop order is, but this can be done systematically, yes.
So you used to make boundary value problem, and what I thought when I saw this in the first thing is usually standard name in theory of PDEs,
Sure.
and so on, but you use it in a very different way, right?
Yeah, in a sense it's
You
different,
use
but
this name very
I mean,
differently, or
what happens between these two scales is, of course, that you solve a system of couple
so you
differential
have
equations.
actually
So
it is actually in the convention.
So this renormalization.
Technically, it is really like
Yeah.
What type of PDEs do you have here?
These are
renormalization group.
yeah,
That's
it's the renormalization
renormalization
group.
group.
Yeah.
That's okay.
So we can stay at this picture. So can you say a little bit more in detail how the running was done? I mean, of the RGs. So where? So yeah. Can you describe it a little bit more?
Okay, I will
The
try.
running of your RGs.
So I'm not entirely sure what the question is, but I will try.
Yeah.
So what we do is here we calculate simply the running parameters from experiments, and we do the matching. And
So you are doing it bottom up.
for the gauge couplings and the Yukawa couplings and the Higgs vacuum expectation model, because these are known at low energy, or they can extract it from experimental data. So they are fixed here with one loop threshold corrections. And then we use the full renormalization group running of the 2x doublet model to evolve it to the supersymmetry gradient scale. And here, in this step, we fix a lot of parameters in the NMSSM. As you probably know, there are a lot of parameters in supersymmetric theories. And these are fixed as the running parameters in dimensional regularization at this scale. So there's actually an interesting point when you do this matching, and that's that, dimensional reduction. So here we renormalize using MS bar, so dimensional regularization. Here we use dimensional reduction because dimensional regularization breaks supersymmetry explicitly. So when you calculate these threshold corrections, you actually get some terms that solely account for the fact that you are switching your regularization scheme. And yeah, so here we fix the DR bar parameters, and then we simply, we do this matching, of course, to fix the parameter, the gauge couplings, Yukawa couplings, and the Higgs length.
But you are basically doing the running bottom up.
Bottom up, and then when we're here, we go back, and then we iterate. So this is this process is iterated until the parameters don't change anymore. And then in the end, the Higgs mass is actually calculated at this scale.
So what about choosing the randomly at the very high scale in the NMSSM, the parameters, running them down, fitting them to the standard model electroweak parameters?
So one of the ideas here is to predict the couplings. Yeah, okay, we'll do that still. I guess that is actually a valid approach. The problem here is that we really need, so for this specific calculation, we really need to know the gauge couplings and Yukawa couplings in the NMSSM, because we're using this full mass matching. So if we want to use that approach, we have to somehow calculate this coupling in this model, and since they are known at low energies, it seems reasonable to calculate them first in the 2x doublet model, then evolve, and then calculate them again. But I mean, I guess with some computational power, you could probably do some exclusion with the approach that you mentioned.
Yeah, I think that you need a lot more compute power.
You cannot run it on this
Exactly. I've been involved in a couple of studies where we actually have done it in that way. I mean, you start at the random parameters on in the higher theory, and then you run it down and compare with the electroweak data, and then if this is a good point to say it, but otherwise, I mean, you go backwards and you
Yeah, I think I saw something similar where they sort of then go ahead and calculate the probability of certain regions in parameter space.
Because are you able to make any predictions then from?
So one idea of this calculation is to predict the scale of new physics. So to say that, okay, in a region where we actually hit the Higgs mass that we have measured, that should correspond to the correct supersymmetry gradient scale, if supersymmetry is correct. Of course, this plot is somewhat simplified. There are, of course, some uncertainties around this, but we can try to estimate it.
How much of this energy region is still
around? There are actually some. That's not a simple question to answer because there's so many parameters in supersymmetry.
But the parameter space has also been drastically reduced.
Yeah, that's true, but so you can't really say that it's only for a SUSY scale above
No,
1
okay,
TeV, because you have scenarios like split SUSY.
I understand your point.
But I mean, of course, I mean, there are a lot of people who have been doing supersymmetry for their whole life, and they are starting to do presentations on astroparticle physics. So there is some significant exclusion of these type of scenarios.
Yeah.
And in fact, I won't be focusing too much on supersymmetry either when I go back to Aachen. It's rather more general matchings of theories and this kind of thing, not necessarily supersymmetry.
Yeah, I'm very curious, can I ask one? You said that already. So what is your bet on the video?
I think you
see supersymmetry one day.
I think
experiment.
I think you have.
So what?
Yeah, it's good that you qualify the question, because I think it's going to be extremely difficult to kill supersymmetry, because you have string theorists who don't care what the scale is. I mean, it could be a very high scale, but they simply need it for the superstring. But low-scale supersymmetry, I think, starts to become very unlikely. And in fact, we are already starting to get more and more scenarios where the hierarchy problem, so the problem of maintaining small corrections to the Higgs mass through supersymmetry, is, well, there's something called the little hierarchy problem, simply because the supersymmetry breaking scale becomes larger, and then the corrections are actually not that small anymore, and you can't really solve this problem anymore. And there are a lot of people who are abandoning all this naturalness, all these naturalness arguments and so on. So I think it's rather a pessimistic view on supersymmetry.
Community is shrinking.
Yeah. Definitely.
Can I ask one more quick question? So in these plots you have bunch of parameters that you choose to take some values, like the couplings, and then you say take xt to be minus 2 times m
Right.
sushi and so on. So how do you choose these parameters, and how much variation do you have in these plots if you were to?
So the parameter that you're referring to, xt, the mixing of the stops, is actually a very important parameter. If you look at there's another plot where the Higgs mass is calculated against this parameter, and you see quite some variation. I mean, several GeVs. You see this sort of camel-shaped plot. So this is one of the parameters that it's most sensitive to. The other parameters are actually mostly constrained by the fact that you want to have a Higgs boson that you can identify with the standard model Higgs. So that's actually not too simple in this scenario. And then, of course, you have all these problems that you don't want tachyons and this kind of things. So these are actually more important constraints.
Okay. Any further questions? Okay, if not, then thank them again.
I also want to thank the committee for taking the time to come here during the summer holiday.
Welcome. So, yeah, Edwin, Jens, and me will meet here for a while, and then the rest of you can wait outside, or at least you better.
Yes.
Maybe coffee.